So first off, are there questions from homework stuff? Yes?
I think it's 123 from the review. Chapter 3.
Oh yeah, good. It's so guys, everybody, even this little group right there. All right, we had a big discussion a while back about homework, and it's apparent that some of you guys maybe have gotten your hands on even beyond the solutions they give you in this book, and that they're out there. I know there's like pirate bays of textbooks and stuff and solutions. I don't care if you get 100 on the homework. If you didn't do it yourself, it's not going to help you, right? And a lot of you guys are doing the homework honestly. It's better to have me give you, say, correct mistakes, and you've honestly done it because you're getting it into your head. I don't understand the people. There are people out there that are copying either from an online solution manual or from somebody else. It's not doing you a damn bit of good, right? The reason I say this number 123 is a very strange one, and I have people getting the right answer out of nowhere, which is neat. Written the exact same way as the solutions manual would have it, which is really low probability that this is happening. Yeah, probability, holy shit. So it tells you, and this is number 123, and this is page 213. The one about all the licensed drivers and all kind of stuff. The percent of licensed U.S. drivers that are female is 48.6. Right? So you get licensed. There's drivers. Of the females, 5% are age 19 and under, 81% are age 20 to 64, so forth. So for example, if I did create a table, they say create a table or a tree, and I think the table might be easier. We got females and males. We got 19 and under, 20 to 64, 65 or over. All right. So we know that the females is 48.6% of the U.S. drivers are 48.6%, so 0.486. So what would I put here for the men? Yeah, the rest of them, right? 48.6, so the rest of them must be 51.4 to make a total of 100%. I like it. There's going to be one here. These are all going to be percentages. That's what's weird about this table is they're already percentages. So, of the females, so of this 0.486, what's it say, for example? 5.03% are 19 and under. So, of the females, 5.03%, where'd it go? 19 and under. So what's that word of mean? Multiply. So 5.03% of 48.6% would go here. So you do 0.0503 times 0.486. Don't do it in your hand. Don't do much. Gotta get my calculator hand installed the minute they become possible. Do 0.0503 times 0.486. That's fine. 0.244. So that's percentage of everybody. So 5% of the females are 19 and under, but there's only 48.6% of them, of everybody, that are females. So 5% of 48.6% is here. You guys see how you have to piece this together? And then let's do one more. Of the females, 81.36% are 20 to 64. So 81.36%. So you do 0.8136 times 0.486 to see exactly what percentage of everybody that is. And that's how you build that table. I like it. Does that help?
Yes.
Good question to ask. If I don't get that question, I get concerned that people are either not doing the homework or they're just skipping this problem. Okay, baby. So you build every element like that. And of course, if you get that one, you know what that one is. They just have to add up to be 0.486, don't they? All right, cool. I like it. And then you can answer whatever question they throw at you. All right. Freaky little problem. I like it. Anything else from homework? Did you get questions about? I feel a little better that question came up. No? Okay. All right. I'm always hopeful for you guys. You know my office hours when they are, right? You can come by. You don't have to make an appointment for that, right? You know, if my office hours are no good, you can email me some extra other times that I could tell you. I'm in there more often, I just have work to do. But if you ask me, hey, can I come see you during this time or this time, I can tell you, yeah, this time will work, I'll make it work. Try me on that. Let's see what happens. All right. Okay. So what we're going to do, we are going to continue in chapter 4. We did, just to remind you guys, we did this whole thing here. If they give me the data like this, all right, so they got to give me some numbers, they have to give me some percentages. The percentages have to do two things. What two things do these percentages have to do? Yeah. When you add them up, you get 1? And they have to be between 0 and 1? I like it. So when I ask you, verify that something I give you is a valid probability distribution, you got to tell me those things. I like it. What will I get when I multiply and then add here? So that says x times p of x. So when I add these up, what do I get? Yeah, the sum of x, p of x. The average, I like it. The mean. And what was the other name for the average, the mean? Expected value, I like it. So when you see expected value, they're actually referencing the mean, because that's for your best guess. I like it. Cool. And then we even went crazy, we did one more column. And this leads to the standard deviation. Let's just write the variance. Alright, so all that's on that handout too. I like it. So we step through it. We know how to use the list now in the calculator, so if they give you a longer list, you don't have to do every single subtraction and squaring and all that kind of stuff. Cool. I like it. If you look at that handout also, I keep asking the same kind of question. How much of the data is within one standard deviation of the mean? I like that question because we have chubby dude and we have empirical. Two theorems about what should be within 1, within 2, whatever. So I love to ask that concrete question because you can just count and you can just see what percentage, not just some chubby dude in Russia going, I think it would be this. You know. That was a horrible Russian accent. I apologize. This is why I teach and I don't do that. Yes?
What was the question that you used this for? You said this.
Oh, they would have to give me these. They'd have to give me these. They'd have to give me these.
I mean, no, like they would ask you a question and then you fill it. What's the question that they asked for you to fill this out? Like you said, like what is the something?
But the bottom line, they have to give you these, or else you can't do anything. So they would ask you find the mean, find the standard deviation, given this distribution. I'm not sure I'm at.
I don't know how to ask my question. It's fine. I'll give it.
Okay. And then that one, you mean this part here? Find the percent within one. Okay. I'll let it go. So what we're going to do now is right on the heels of this. This is a brand new way to present data. So in the early going, in the olden days, we have data like 10, 11, 15, big old list of data. Well, if there's some repeats in that data, if there's a lot of repeats, then I'd rather give it to somebody like this, because then I can say, well, 30% of my data was 10. Instead of writing 310s or something out of 1,000, I can just say 30% of them were 10. You guys see the import of this. I don't want to make a freaking list. I don't want to. I can just tell people their 30% were 10s and so forth. And that's why we developed a way to work it out if they gave it to me like this. I make a new kind of formula to work with it. Now we're going to do even another way to be given information about data. And this is still what's known as discrete. And I don't think I made a point of that. Why is this called discrete probability distribution? Why do you think it's called a discrete? Say again?
The numbers don't go into infinity. Like
I love it. Does it skip any numbers as I go between the data? Did I skip any numbers from 10 to 11? I skipped how many numbers? Infinite number of numbers. What about 10.1? What about 10.0000003? Right? You guys with me? So it's discrete. I don't know if you guys are discrete versus continuous. Discrete was when I skipped a bunch. Right? So this would be the number of children in a room. It can't be 10.3. Right? Even if that kid's having a rough day, you don't say it's 0.3 of a kid. It's still a kid. Right? All right. He's really tired. Let's count him as 0.3. No, he's still a kid, just a tired kid. All right, like, so that's discrete. What's coming up after we talk about this next thing is going to be what's known as continuous. So this would be data that can take on any value in a continuum. And that's when we're going to get more, continuous pictures of data, my true normal curves. Right now I can't really have this because I can't have somebody that has, like I said, 10.7 kids or something. My God, these poor people. Like 10 or 11, I don't know, 10.7, let's just say. I can't keep track of them. I don't blame. All right. So we got one last distribution that's discrete to look at, which means it counts things. And the beautiful thing about this is the formula is so nice, and I know that you're all, yeah, you would say that, you weirdo. But let's give us an example. So here's how this works. And let me go take a step back. There was a problem on the quiz. What's the probability that at least one of them has something or whatever? Like the number 3C on your quizzes, right? So if you looked at that 3C, so a few too many people. So if I had picked 4 people, and I want the probability that at least one is left-handed. Go with me for a second. I want to build up to this idea. A few too many people did this. They said, okay, you can have a left-handed person, and then not left-handed, not left-handed, not left-handed. And then they just calculated that probability. That's way too specific. For a couple of reasons. Let me just stop here for a second. If you're one of these people, I'm not naming names because I forgot who the hell you were, actually. A few people made a mistake. A few people made similar kind of mistakes. This is way too specific. Why does the first person have to be the left-handed? Is everybody cool with my notation here? Yeah. L is left-handed, and of course the prime means not. I don't want to say right-handed because you could be ambidextrous. All right, and like to shove them. I'm ambidextrous. Oh, good for you. Sorry. I am so desperately not. All right, so, but what other way can I do this?
No. One minus the
Well, no, not the right way to do it. What other way can I do it just directly?
L prime.
It's going to be L prime, 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 L. See how that L dude just floats through? Which one is the left-handed one? And in fact, that's not even enough yet. Because I said at least one. So maybe the first 2 are left-handed, or the last 2, or the first one and the last one, or the middle 2, or the first 3, or the first one and the last 2. And holy shit, stop, Jeff, yes. I really want you to understand this is building up to what we're going to do today. But just to remind you, doing it this way, there's a lot of work. It'll work. It would work if you captured every single way to do it, and then multiplied the probabilities and then added them all up, you would get the right answer. My God, why? Right? It's sort of like if I had this table, and I I knew this, and then there were a million other things. A million. Do you understand? A million other entries. And I said, what's the probability that I get something more than 10? Do I want to add all these stupid things up? No, I'm going to do 1 minus the one I left out. That's the general idea that I captured doing this. So instead of doing all this craziness, because I'm not even done, holy crap, I would rather do 1 minus the only thing I left out. What's the opposite of at least one being left-handed? None of them. Yeah, 1 minus probably that none of them were left-handed. I like it. So that's a little insight into 3C if you made a mistake on that one. All right, let me stop there for a second. So 3B builds into 3C. I like it. All right. So let's. So that's this. If I say at least one, there's going to be a quicker way to do it. My God, let that happen. Now we're going to do stuff like, what's the probability of exactly one left-handed person? Stuff like that. Then I can't do 1 minus none, because I didn't say at least one. There's got to be a more direct way to do that one. So let's do this. Let me call the probability that you get a left-handed person, let me just call it P. Just because. I don't want to write L and L prime or P of L. Whatever. Let me call the probability that you get a not left-handed person Q. Okay. And I want to know, if I pick 4 people, what's probably going to get exactly one left-handed person? Yeah. What's that probability going to be? Okay. So this formula is really, let it be nice. You got to see what you guys think. So I already basically did it a second ago, but I wanted to change the variables and see if you could do it also. Using P's and Q's, what's one way to do this? I'm picking 4 people. I want one of them, exactly one of them to be left-handed. So how can you write it? P is left-handed and Q is not. Yeah, so it could be the first one's left-handed, and the next one's not, and the next one's not, and the next one's not. Does that match what I'm looking for? Yes. Is that the only way to do it? Yeah. No. You can do it that way, or, and or means add, I love it, or the second one could be left-handed, or third one, or, and is there any other way to do it? No. I love it. All right, let me let that sink in. Does that on its own make sense? Even just outside of statistics. If I had 4 people and one of them's left-handed, who could it be? The first one, the second one, or the third one, the fourth one, right? I like it. So, mathematically, algebraically, oh shit. Each one of these looks exactly the same to math. And why am I doing, what operation is this, of course? Multiplication. And why am I doing multiplication? Because I want the first one to be left-handed, and the next one not, and the next one not, and the next one not, and means multiply. And of course, just because I put a left-handed person next to you, does that change your handedness? Do you go, whoa? No, so they're independent, right? That's why I'm allowed to just multiply them. Let me let all that sink in. Oh, there was a reason for chapter 3. Oh, shit. All right, so algebraically, what's a better way to write this? It pains me to write it like this. What's the more concise, compact way to write? P, Q, Q, Q. P times Q cubed. So all of these would be P times Q cubed. And how many are there? 4. Good. So there's 1 P. Why does that make sense? Because the question wants me to have exactly one left-handed person, which means how many not left-handers am I going to have? 3 of the others. So 1, what we will call a success. And I'm not saying left-handed people are better than right. A success is just because I'm looking for a left-handed person. If I'm out on the battlefield looking for dead bodies, a success would be a dead body. So a success doesn't mean happy thing, right? It just means what I happen to be looking for. So I would call, this would be probability of success in general. And this would be probably a failure. So if I'm looking for one left-handed person, I want one success and 3 failures. And how many ways can I do that? 4 ways. I like it. So now if I told you that there 11% of Americans are left-handed, could you calculate that probability? 11% would go in for what variable? P. P is my left-handed person, right? So it'd be 4 times 0.11. And what would Q have to be? 0.89. I like it. Cubed. All right, so let's see if you can do that in your calculator. What do you guys get? Go out to 4 places. Uh-oh. What did you guys get? 0.3102. I like 0.3102 is what you should get. Just put in there 4 times 0.11 times 0.99 to the third. Yes?
Why are you multiplying by 4 with, like, you're saying 11% of Americans are left-handed, but before we were only looking at 4 people?
All right, you ready? I really want to make this connection. So if I said, like on the quiz, I said I had something like this. I want the first one to not like something, the other 3 to like it. Or something I said the first 2 to like it and the last 2 to not like it, right? Is everybody cool with that? You all had that on number 3 on your quiz. Is that cool? So, if I said I wanted the first one to be left-handed and the other 3 to not be left-handed, we would just calculate that probability. We would just do 0.11 times 0.89 times 0.89 times 0.89, right? That's exactly how we would do it. That's how we did it before. So why are things new now? Because I'm not being as specific. I didn't say I want the first one to be left-handed. I said I wanted at least, in this case, thankfully, I'm just saying I want exactly one of them. So is this the only way to do it? No. You could do it this way, or that way, or that way, or that way. So now I have to add up all the ways. They all look the same. They all look like 0.11 times 0.89 to the third power. Right? So let me make sure. Guys, get this. This is beautiful. So if I had 80 people, and I wanted exactly 11 of them, let's not make it 11 because it's all exactly 20 of them to be left-handed. Lefties. Please, dear God, do you understand how long that list would be? Do you start to comprehend how long that freaking list would be? Holy shit, it's longer than you even think. Because maybe it's the first 20, or maybe it's the last 20, maybe it's the middle 20, maybe it's the first 2 and the last 18, maybe it's the first 7, the middle 3, and the last 10. Holy crap. This list was nice. There's not that many ways to do it, so that's what that number is there. But even though we don't know what number goes here, where the 4 is, we don't know where number goes there, but that number would mean what? What's that 4 mean? How long the list is, how many ways there is to do something. This number I don't know yet. I'm going to show you how to calculate it. That's the only part that we need the calculator to help us on. But what's this going to look like? What are the powers going to be here? How many successes do I want? 20. How many failures?
60.
The rest. 60. This part is always easy. Always. The part that we need help on is, I don't want to make that list. Dear God. That would take, literally, maybe a few days to just sit there 24 hours a day, just writing them out. We'll see how long that list would be here in a minute. I'll show you. Let me stop there for a second. You guys kind of with me. So the important thing to really, really get is this piece. That piece is the piece that makes unbelievable amounts of sense if you let it. I want exactly 1 success. So that means I have 3 failures if I have 4 people. So 1 success, there's a first power there, right? 3 failures, all I need is how long the list would be. We did the list, we know it's 4, beautiful. This one, oh crap. I know I want 20 successes. That means I have to have 60 failures because there's 80 people. The only thing I need help with is how long would that list be? I'm going to add them all up, so the coefficient is going to be how many there would be. Okay, all right, maybe. So let's see. So here's the thing. Here's how this works. This is the one of 2 things this semester that I'm going to totally do on the calculator. And what it is, it's called combinatorics. It's actually called combinations. But I just call it choose for short. Right? How many ways is there to choose one person, one spot out of 4 spots? There's 4 ways to do it. Does that make sense? So what do I need here? I need to know, out of 80 spots, how many ways is there to choose 20 of them? And I'm writing it that way because that's the way it's going to look in the calculator when we look this up. Alright, let me stop there for a second. I love the looks of it. Alright. So this is going to be stupid big. But what would this be, real quick? Let's get that 4 back again. What would that look like? I have how many people, how many spots? 4. And I want to choose how many to be a success? 1. So if we do 4 choose 1, it better come out to be 4, or else we can all go home. And when I say it, somebody's like, please, calculator, have a mistake. Just going to let us go home. So if I do 4, yes, Jeff, we got the 4 of it. Trying to make it, you guys can see that, all right? Now go to math. Zoom out a little bit. Go to your math button. Bam. Go to probability. So we're going to turn this on. Let me see, where are you? There. Oh, that's freaky looking. Oh well. Just can't win. Oh. So is everybody with me? You got the 4 in there, hit math. Now go to probability and CR. Right? Not National Public Radio. We want NCR. That's the one that stands for choose. N is the total number of things. And they use the letter R for this. We're not going to use the letter R for this number, but we'll see what we use. So if I put in there 4, choose 1. If you have the newer calculator, it'll look like that. I think the older one just puts a 4 NCR 1. Oh well. You get 4, right? Is everybody cool with that? So now if we try 80, choose 20. Do you understand what that means? Let me put it somewhere you can see it. What does that mean? 3.5? Like 3.5? What does that mean? Oh, so if you had an error, you have a TI-82?
Okay.
That means times 10 to the 18th power, right? So you move that decimal over 18 times. That is how long the list would be for this problem. But do you understand that the idea doesn't change? How did we get that number 4? We made the list, and we got the number 4. Well, how do we get the number that we're going to put here? We let the calculator count it, because that's what calculators do. They're pretty good at counting. It did that pretty fast. I'm like, ooh, I'm impressed. All right, so here's how. Let's see if this will work. I don't know. This might be too extreme. We're going to try to put this whole thing in the calculator at once. Because think about it. What happens when you multiply a number smaller than 1 by another number smaller than 1? Normally, when you multiply numbers, they get bigger. But if I did 0.5 times 0.5, that is 0.25, right? So if I do 0.11 to the 20th, 0.89 to the 60th, multiply those together, that's going to be stupid small. Or whatever your favorite adjective is. Stupid seems to be mine, for the most part. Times stupid big. Comes out to be normal. So here's how I would do it. I would do, 80, choose, 20, hit over if you got the newer one, times 0.11 to the 20th, hit over to get out of the exponent if you have the newer, times 0.89 to the 60th. This might be too much
You
for
didn't
you.
get out of the exponent
Oh, that so sucks. Where did I not get out of this?
after 11 to the 20th.
No, I did.
Oh, I just didn't see that inside.
My bad. Yeah, poor little dude. Now what's that mean? So when I do this, I get 2.186 times, so it's times 10 to the negative 4. Who remembers this scientific notation? What do you do?
To the left.
Yeah, move it back. 4. So once and then 3. So it would be 1, 2, 3, 2, 1, 8, 6. That's the probability. If I had 80 people, that exactly 20 of them would be left-handed. That's the probability. Now we're not quite there yet, because it's a little more involved than this. But can you see how this, if I knew that about 11%, and that is the current best known estimate for the percentage of left-handers. How many guys are left-handed in here? Not me. 1, 2, 3, 4? Out of about 44 people, let's say, that's 1/11, which is, I don't know, about around a little bit less than 10%. It's pretty close to 11%. Let me stop there for a second. So if I know that 11%, I can, and I have 80 people coming to a conference or something, I can estimate how many left-handed chairs I want to put in there. Like, there's always a certain number of left-handed chairs. I think these are supposed to be, bless you. Yeah, these are supposed to be ambidextrous. They are a little too weird for me, but. All right, so let's do another example. So a very small chance that I'll have 20